Okay, officially good morning. So let us now start the lesson. The first thing I want to talk, these are very simple ones, so I will go a little bit quickly. But if you have questions, please stop me. So the first thing we want to talk about is that what is the meaning of image and inverse image of a set under a function? Okay, so that's what we want to define first. So the first one is definition of image of a set. So let us say that I have a function from a set A to a set B. So if you want to visualize it, something like this. Here I have A, here B. B. A is called the domain and B is called the codomain. Okay, and then what we do, we take a subset of the domain, any subset that you like. For example, B. And now you know that usually when I talk about functions, a function f of x equals to x squared, I can ask you what is f of 1, what is f of 2. But here we want to talk about what is f acting on a set. Okay? So here E is a subset. E itself is a collection of elements. And I want to define for you what do I mean when I write f acts on a set. Okay, so that the answer is very simple. This set includes some points in it. Apply f on the points and find the images. That collection is f of E. So it means that, for example, I have this, I apply f on it, and I have another point, I get another point, I get another point, you know, and then if I collect them here, this is called f of E. If this is that right? So mathematically, f of E means what? F acting on x such that x belongs to E. So that's the definition. Okay? So if you want to do the first example, so here I have given you this example. A is equal to minus 1 and 0, 1 and 2. And I have given you B to be set of integers. And I have defined a function for you in the form of ordered pairs. I hope that you have studied that in the preliminary part yourself. So the function is defined to be minus 1 and 4, and then 0 and 1, and then 1 and 4, 2 and 9. Yes? So are you familiar with this way of defining a function? Yes, function is when I say I have a function from A to B, what does it mean? It means f is a subset of A cross B, Cartesian product of A and B, but in a way that no ordered pair has the first component the same. So if I have a relation, I can have the first components repeated sometimes. But if I am dealing with a function, no one of these first components should be repeated. That's the meaning of a function from A to B. So in that case, if I ask you what is f of minus 1 in this notation, what is f of minus 1 is 4. What is f of 1 is 4. So the outputs could be the same. So it's already indicating that this function is not injective. Because even though these inputs are not the same, but the outputs are the same. So this function is not injective. Okay, so here, this function is given. And this set, now I have a subset of A. This is my domain. The subset, according to the problem, is minus 1 and 2. And I am asking you, what is f of E? Okay. I hope that you understand this is the new concept because f is not acting on a number or an element. It is acting on a whole set E. Okay, so what does it mean? It means that I have to apply f on each one of these. So this means this becomes f acting on minus 1, f acting on 2. And I go to the definition of my function. What is f of minus 1? I see f of minus 1 is 4. What is f of 2? I see it is 9. So that's it. That's the answer to this one. Understandable? Very simple. Okay, so now let us go to the next example. So this example is a continuous one. So let me do it on the board here. So f of x is given to be 2x plus 3, and then I have given you that the function f is of course defined from R to R, and then I have given you b to be the closed interval from -1 and 2. I am assuming that you know intervals. Of course, at the end of this, I will introduce you formally. So we want to know what is f of e. Yes, so this is example 1.3. So what should I do? So f of e, what is the definition of f of e? F of e means f of x where x belongs to e. E in this case is -1 and 2. Yes? And then what is f of x? F of x is also 2x plus 3. So it means that the set of all 2x plus 3's where x belongs to -1 and 2. I don't want to make it so hard, but can you write this explicitly? It means that you choose any element, every element from this closed interval, and then you multiply it by 2 and add 3 units to it. And then collect them in a set. So what will happen here? Can you, I mean, this is just a definition, but you have to do a little bit of computation. Can you guess what happens? If x is between -1 and 2, so if you multiply it by 2 and add 3 to it, it becomes 4 plus 3, 7, and it becomes -2 plus 3, 1. Yes? And of course, I hope that you agree this is the case. So it means that what can I write at the end? I am a little bit sloppy because I have to prove everything. I have to prove. So can you guess what the answer is before I say something? Yes?
The range of 1 to 7.
Closed interval from 1 to 7. Yes, I am a little bit sloppy because you know that this equality is between two sets. And whenever I want to prove that two sets are equal, I have to prove that this one is a subset of that one, this one is the subset of that one. But I am relying on your intuition that in this case it works. Is that right? For example, if I have given you this function, let me keep this the same. Let me give you this function. From R to R, let me test your intuition now. And I give you f of g of x is equal to x squared. For example, okay, can you tell me what is g of e in this case? You have numbers from -1 to 2, but this time you are supposed to square them. Yes, please?
0 to 4.
0 to 4. Yes? 0 is included, 4 is also included. Is that right? Understandable? Okay. So there is a theorem here that it is good to know, okay? So we want to see how images of unions and intersections and differences are. Okay, so I will prove one part of it for you, and then you can work on proving the other ones. So let me prove part 2. So so what does it mean? It means that, so this is theorem 1.4. So if I have a function from A to B, and I have two subsets of my domain, E1 and E2 are subsets of my domain, I want, for example, to see what happens if I union them. Yes, it becomes a new set, but definitely this is also a subset of A, because if two sets are subset of A, I union them, the union is still a subset of the domain, so it makes sense to talk about this, okay? And it also makes sense to talk about them individually. And the natural question is that, is there any relation between these two? The answer in this case, yes, they are equal. So somehow you can say that f of the union is f of the first one union of f of the second one. But as you see for the other two cases, this is not the case, okay? So for intersection, f of E1 intersect E2, I want to show that this is indeed a subset of E1 intersect of f of E2. There are some that we can talk more. We can say when the equality happens. Equality happens if and only if f is injective. But these are not part of the course, so I don't want to distract you for these things. But if you are interested, you can work it out. And the other one is f of set difference. And that symbol is not very ubiquitous in mathematics, but this is also used. So what do I mean by this symbol? So a subset of B is equivalent to saying that B is a superset of A. So when you see that symbol, it means the other way around. So here I have it as f of B1 minus f of B2. Okay? But let us, for example, prove part 2. Okay? So, how can we prove part 2? We want to prove this. Again, so you want to prove an inclusion at the level of sets. This is a set, that's also a set. You want to show that one is the subset of the other one. The best thing is to choose an arbitrary element from here and conclude that that element is also in the right-hand side. And because usually, you remember, it's a convention in mathematics, the domain elements are typically denoted by X, the codomain elements are typically denoted by Y. So if I want to choose a letter, I prefer to choose Y. Okay, so I would say let Y belongs to f of E1 intersect E2. We prove that. Okay, help me. What should I write? We prove that what?
It's also it's in the other one.
In the other one. F of E1 intersect f of E2. Okay, this is what we want to do. Okay, but then you need your definition. So you are telling me that Y belongs to f of E1 intersect E2. What can I conclude from this sentence? According to the definition of f of acting on a set, there exists what? Y is in the f of a set. It means that there was an element in this set, so when f acts on that element, it becomes Y. That's the meaning. So when you say Y belongs to this, it means there exists an element X where, in this set, such that what happens, Y is equal to f of that X. You agree? That's the meaning. Okay, but then let us analyze this a little bit. When you tell me that X belongs to A, E1 intersect E2, what can I conclude? I can conclude that X is in both of them. So this means X belongs to E1 and X belongs to E2. Okay? Now I hope that you can see it is finished. So let me save word, let me write here. X belongs to E1 and Y is f of X. I want you to fill the gap. X belongs to E2 and Y is f of X. Okay, can you tell me what can I conclude here?
F of E1.
What is f of E1?
It's Y.
Y is f of an element, that element is in E1. So this means Y belongs to f of E1. Do you agree? Yes? And then this means that Y belongs to f of E2. And this is AND. Okay, now Y belongs to two different sets simultaneously. So what I can conclude that Y belongs to the intersection, yes? Yes. So these kinds of proofs you need to know in analysis. Understandable? Very simple, straightforward. Okay, but the question is that, Bobak, how do you think that, so how should I be sure that this is not equality? Because still there is a chance that this is equality, yes? And the next example shows that, no, give a counterexample that sometimes it is indeed not equality. So that is the topic of the next here. Give a counterexample for this one. We want to really show that in some cases, equality does not happen. Equality for union always happens, but there is no guarantee equality happens for intersection. There is no guarantee that equality happens for difference, and the side of the inclusion is different for the intersection and for the difference. So, any ideas? Try to think as a very simple example. So, example 1.5. So for example, let me write f from R to R, and f of x ex squared. Yes, and then let me write E1 to be just the set with -1 and 0, and then so let me see if it works or not. Yes, and then E2 just 1, for example. Yes. Okay, do you agree that this works? Let us check. Well, how should I check? E1 intersect E2. What is that? Empty. So this means that f of E1 intersect E2 becomes f of empty. But what is f of empty? So what was f of acting on a set? You have to apply f on all those elements, but empty doesn't have any elements. So what's the answer? It's the empty set. Okay? But now if I calculate, if I have f of E2, f of E1, what is f of E1? F of E1 means apply f on the elements of E1. F is a squaring function, so it becomes 1 and 0. And if I ask you the same question, what is f of E2? F of E2 becomes 1. Yes? And now if I intersect, it becomes just 1. And then you see that they are not equal. But if you want as an extra exercise, you can prove that if f is injective, then the other way around is also correct. Any questions?
So you mean if it's injective, then they are equal, or
they are equal? Yeah. Okay. So now the other definition is the inverse image of a set or a pre-image of a set. So here I started with a subset of the domain for image. For pre-image or inverse image, I start with a subset of codomain. Yes. Okay, so if you have a set, if you have a function from A to B, again, if you want to visualize it, you can visualize it like this, A and B. But this time, I give you a subset of the codomain. Yes, let me call this one H. And then I want to talk about F inverse of H. Okay, and this is a little bit confusing. Because this notation is a little bit, it's not 100% good notation, because usually when you write F inverse, you already think that the function should be invertible so that I can talk about F inverse. But be careful. So it's you shouldn't get confused, because when you have F inverse and you have a set in front, it is not the inverse function, it is the inverse image. Okay? And for this makes sense, you don't even need the function be invertible. So this is at set theoretic level. So what does it mean? F inverse image means find all elements here that are mapped inside H by F. So it means this is the set of all x's where in the domain, so that when you calculate f of x, it belongs to H. Okay, so that is called the inverse image of H. So this means that you are interested in those elements here, so that when f applies on them, it takes you to the H. That is called the inverse image of your subset H. Is the definition more or less clear? Okay. And then again, you don't even need to have F inverse to exist. You don't have to have your function invertible. So any function, we can talk about F inverse of any set, any subset of the codomain, even if the function is not invertible. Okay? So I have, for example, can you tell me what is F inverse of B? First of all, does this notation make sense? Yes, because B itself is a subset of codomain. By F inverse of B, I am asking you, can you tell me the elements in A that are mapped to B? But what are they? Just A itself, by definition of the function. Yes?
So what if, because B is not the range?
So B is not the range.
So what happened? But then couldn't there be, or no, you removed those.
No, because the definition of a function, it means that from all these things, you should have an arrow coming out.
Yes, but I mean, couldn't there be, if you have a discrete function, for example, but then your codomain is R, that means that there are some B's, a lot of values in B
That are not covered.
that aren't covered, but that doesn't matter because
That doesn't matter. Because you are considering the whole bunch of it, some of them are not covered.
Yes.
And then you are asking, tell me the set of all elements that are marked there.
Okay.
Of course, in those elements that are not image of anyone, they don't have it. So that is always true by definition of the function. Because when I write this in our conventions, A is always the domain.
Yes.
And it means that every element of A should be in the domain.
Yeah.
So there are not elements in there. So that's always true.
So it's the same notation as it means the same thing as
We had in algebra.
Yeah.
Exactly. Okay, so for example, it is still on the board, so let me just do it here. The next one, example 1.8. So we want to calculate F inverse of H if H is 4 and 9. Here I mean this example which is still on the board, yes? Yes, that's up there. The discrete F up there. Okay, so if I want to solve this, if I solve this, I would say F inverse of H. What is the meaning of this? It means the set of x's coming from the domain. What was the domain? Domain is A, which is -1, 0, 1, and 2, such that when F acts on X, the answer becomes an element in 4 and 9. So this is just how to read this. So I am just plugging the information in the problem into my definition. Here, capital A is given up there, and capital H is given in the problem. So I have just copied and pasted this definition for the information of the problem. But then you have to ask yourself, I am looking for all x's coming from here, but not all of them. The ones that F acting on X give me an answer in 4 and 9. So what are the answers? Can you just read it and tell it?
-1 and 2.
What is that?
-1 and 2.
-1, yes, and 2, but more. -1 and 1 and 2. Yes, because 1 also is mapped to 4. So it is -1 and 1 and 2. Is that right? That's the F in. A very simple idea. Okay, so let us do the other example here. So F is this function. F of x is equal to sine of x. We want to determine F inverse here. And you see here, for example, sine x is a famous non-injective function. So it is not invertible on 0 and 2 pi, but still it makes sense to talk about F inverse. So, example 1.9. So the function F is from 0 to 2 pi to R. F of x is equal to sine x. And you know that this function is not invertible on this domain. We have to restrict the domain so that we can have arc sine function. Okay? So this function is not invertible, but still, I am asking you to answer this question. So -1, 0, and 2. Okay, so how should I answer this one? Let me write the definition here. So F inverse of that set, -1, 0, and 2, is equal to, first let me put the definition. All x's coming from where? Coming from my domain. In this case, my domain is this. Such that f of x, in this case sine x, belongs to -1, 0, and 2. Okay? So I am interested in those values here, so that when I calculate sine of those values, it turns out a number inside this set. Okay? So, for example, can you just tell all of them? So let us see when sine x becomes -1. You are working in this domain, and you want to make sine x equals to -1. How many possibilities I have? Sine x becomes -1 is 3 pi over 2, 270 degrees. This one, and this is the only one. And I want to make sine x equals to 0. How many choices I have? 2. 1, 0, and 1, 2 pi. I will add them here. And then I want to make sine x equals to 2, which is impossible. So it means that I end here. Yes? So this is impossible. But it doesn't matter. I have it still here. Understandable? Okay. And we have a similar theorem for F inverses, inverse images. And the good news is that all of them are equality here. Okay, so there is nothing that we have to be careful about. Okay, so let me prove one of them, for example. If you don't mind, let me prove the union part now. So, theorem 1.10, proof of 1. Okay, so if I want to prove this, how should I prove this? I want to prove that F inverse of the union is equal to F inverse of the first one union F inverse of the second one. This is what we want to prove. So again, this equality is equality between two sets. And if I want to prove that two sets are equal, I have to prove the inclusion, one from left to right, one from right to left. Is that right? So I need to choose, how should I start the proof? I would say let, can you help me the first sentence? Let what? Let something here, okay? But this something, is it better to call it X or call it Y? Of course, you can call it whatever you want to, but if you want to follow the tradition, what should I call it? X or Y or what? Yes?
Y.
No, X. Because be careful, F is in the codomain. F acting on a set takes me to the codomain. F inverse takes me back to the domain. And usually the elements of the domain are called X. So it's not important, you can call it whatever you like, but it is better to do more traditional. So I would say let X belongs to what? F inverse of H1 union H2. We prove that. We prove that X belongs to F inverse of H1 union F inverse of H2, yes? This is part one, because there is another part. The other part is that then I have to choose X here and show that X is there. Okay, but let us start the definition. It's very simple. So I start from here. X belongs to F inverse of H1 union H2. So what does this mean? Can you translate it for me according to the definition? When you see X is in F inverse of a set, it means F of that X belongs to that set. So this means that F of X belongs to H1 union H2. Do you agree with that? That's the meaning, that's the definition. But if something belongs to the union, it means that thing belongs to H1 or the other one. Fx belongs to H2. But tell me, if someone tells you f of x is in H1, what can you conclude about x? Where x lives? X is somewhere, but after f applied on x, you find yourself in H1. So where was X?
In the domain.
It is in the domain,
Yes.
but more restricted. I hope that you are not confused, you know. So is this a step clear? That's the definition of F inverse. When you say X is in F inverse, it means when I apply F on X, I will find myself here. That's the definition. And from here to here is just a definition of the union. But now I am telling you, forget about this. I am telling you X is somewhere in the domain. But when I apply F on that, I will find myself within H. So where is that X? It's just it's yes.
The inverse image.
Yeah, exactly. So it's like a circular loop. You know, X belongs to F inverse of H. Do you agree? Or what can I say about the other one? X belongs to F inverse of H2. And then what can I conclude from these two? I have one element. I know this element is either within this set or within that set. So I can conclude that it is definitely in the union. Yes? So X belongs to the union. Okay? And I want to give this as an exercise too. You have to complete it yourself. Because so far, I haven't proved the equality. I have proved that the left is a subset of the right. You have to do this the other way around. In the case of intersection in that part, it was not working. You can see, you can write the proof and see it doesn't work backward. But if you write this, by the way, you can immediately cheat a little bit. Can you cheat immediately? Yes?
If it's equality instead of implication.
Yes, I can go backward. Equivalency. Yes. So it means that it is very, do you agree that from here I can go backward? It's easy to convince yourself, yes? So I can go backward all the time. It is very good to try to go backward here to see where you cannot go backward. Okay? That is the obstacle that you couldn't prove equality. So in principle, let us finish it, okay? Okay, so now let us go to the next topic. So that's a very important one, supremum and infimum. So let us discuss this a little bit here. It's a very, very simple topic, but we want to talk about supremum and infimum. So let me write the title here to save as much as I can. Okay, so in order to talk about supremum and infimum, supremum means the least upper bound, infimum means the greatest lower bound. So let us talk about what do I mean by an upper bound, what do I mean by a lower bound. Okay, it's a very, very simple concept. So here let us say that this is the set R, all the numbers, and then you have a set, one part of it is a set. For example, this is your set, subset of R. So let me call it E. Okay, so it means that E is this set. Any number on the real numbers which is greater than every element of E is called an upper bound for E. Okay? And every element which is less than every element in E is called a lower bound for E. Is that clear? A very simple idea. So, for example, if I give you this set, let me write it as for example, let me write it as 1 and 5. Let me close it. So, can you give me an upper bound for E? It means give me a number, a real number, so it is greater than or equal to all elements of E. That number is called an upper bound of my set. For example, do you agree that 7 is an upper bound? Because every element within E is strictly less than 7. Can I say that 5 is an upper bound? Yes, because every element within E is less than or equal. So bound means less than or equal. So 5 is also an upper bound. But you already see that can I make the upper bound smaller than 5? 5 is the smallest upper bound, which is called the supremum. Is that right? And in this case, supremum belongs to 5, belongs to set itself. If I ask you what is the maximum of elements in E, what do you answer? What is the maximum element of E? 5. What was the smallest upper bound was also 5. Okay, but let me ask you, can you give me any lower bound of my set?
0.
0, for example. 0 is a lower bound because every element 0 is less than or equal to every element in E. But what do you think about 1? Is 1 is also a lower bound?
Yes.
Yes? Yes, because any element in this one is a little bit larger than 1. So it means that 1 is still a lower bound. But can I choose a lower bound greater than 1 for this set? Even if I go slightly over 1, there are a lot of elements of E which are below that element, that number. So this is the biggest, this is the largest lower bound. The largest lower bound is called infimum. Is that clear? In this case, what is the minimum, by the way? So let me just write them for you. So in this example, if I ask you what is the maximum of E, you could answer. The maximum is 5. If I ask you what is the supremum, this is the SUP, supremum is still 5. Okay? But if I ask you what is the minimum, that is the reason that we are interested in the notions of supremum and infimum. If I ask you what is the minimum, if I ask you what is the infimum, you already answered. Do you agree? Among all lower bounds of E, 1 is the greatest one. Yes? So that was 1. But if I ask you what is the minimum of E, what's the answer? There is no minimum, so it does not exist. Do you agree? Because let me make it clear for you. This is a hollow circle, means that 1 is excluded, and then let me fill it up. It is 5. Okay? So 5 is the maximum should be in the set itself. But I cannot say 1 is the minimum. First of all, it is not in the set. And if I say that there is no minimum, if you say that, okay, 1 is not minimum, but this number is minimum, that is not correct. Yes, because I can find a smaller than 1. If you say, no, this one is the minimum, I can still find a smaller one. So there is no minimum. So for this set, I do not have any minimum, but still I can talk about infimum. So infimum is something similar to a minimum for the cases that we cannot work with the minimum. Is that clear? Okay. But this is, of course, if a set is bound, so if a set has an upper bound, we say that it is bounded above. If it has at least one lower bound, we say it is bounded below. And if it is bounded above and bounded below, we just simply say it is bounded. These are just names, okay? But this is not guaranteed that every set is bounded above or bounded below, okay? For example, the set N, 1, 2, 3, etc. Do you think this set is bounded? Is it bounded below? Yes, because if you say it is bounded below, you need to tell me what is a lower bound. Can you give me a lower bound of N? 1 is a lower bound. 0 is a lower bound. How many lower bounds we have? Infinitely many lower bounds. Yes, any number 1 or smaller is a lower bound. But do I have an upper bound here? So it is not bounded above. Okay? So if it is not bounded above, we can say that this set is not bounded. Okay, what about this set? For example, if I have E, 1 minus 1 over N, N belongs to N. This is a good example. It's not hard, but it's good to intuitively understand it. So let us talk about minimum, maximum, and so let me, yes, that's an example. I have written it there. So this example, let us see that. What do you think about this set? Do you think it is bounded above or bounded below or whatever? We want to talk about all these concepts for this set. So let us visualize it a little bit. Okay, so if N is equal to 1, I get 0, okay? But if n is greater than 1, what happens? 1 is here, 1 minus 1 over n, so 0 is here. So if I choose n equals to 1, this element becomes 0. But if I choose n greater than 1, for example 2, 3, I will end up somewhere here because this is 1 minus a little bit. So this is 1 minus 1 over n. Okay, and then you will start increasing n, 3 and 4, and then write the elements of your set. What happens? When you increase n, this starts moving. It moves towards 1 because 1 over n becomes a smaller. So this means that because this difference is how much? This difference is 1 over n. When you increase n, this distance becomes a smaller. So this means that this point starts moving towards 1. Okay? But it will not go beyond 1. Do you agree? So is this set bounded above? Yes, because it cannot go beyond a threshold. So it is bounded above. Is it bounded below? Yes, because the smallest one is 0 and it cannot go below. So it is bounded above and bounded below. So can I say it is a bounded set? Yes. But now let us talk. What do you think about minimum? What is the minimum of E? Minimum should be something that is attained. It should be inside your set. Okay? What is the smallest number within your set? 0. Okay? But what about infimum? Infimum is the largest lower bound. So it means that you come from left, the first time that you are stopped with the elements of the set, that is somehow your greatest lower bound. So what is the infimum here? 0. But now let me ask you, what is the maximum of E? Now be careful, maximum. Maximum should be attained. Do you think that at some point I reach exactly on 1? No, because I am making n larger and larger. Is it possible that at some point this becomes equal to 1? No, it is not possible because this means 1 over n should be 0, but it cannot happen. 1 over n is not 0, okay? So this means maximum does not exist. Because I can get closer and closer to 1, so there is no single number in my set which is the largest one. Whatever you tell me within the set, I can find something more. Yes? So, but what is the supremum? Can I talk about supremum here? What is the supremum? 1. So I hope that you understand the difference between supremum and maximum. So the good news about supremum and infimum is that as soon as you have a bounded set, you can talk about them, even if the maximum or minimum does not exist. Okay? So just read this remark and I will stop. Yes. So the remark, this is good to read. Okay, so an upper bound does not need to belong to the set. This is important to know. And a maximum must belong to the set. Okay, so this is important. For example, 1 is an upper bound of this open interval from 0 to 1, but 1 is not the maximum of that set because 1 does not belong to 0 and 1. Similarly, you can say something about lower bounds. Okay? Okay, so let us stop and have a little bit of rest and then we come back. Thank you.